Welcome to my class 12 Physics, first chapter, that is electric charges and fields. And the main point of discussion today, that is electric flux. What is the meaning of electric flux? And before that, we will discuss about what is the meaning of area vector. For area vector, we write the symbol that is del S vector. Del S means small area element. Del S means small area element. Suppose we take a small area element. This one is a small area element, and electric field lines are also there, and these are the electric field lines. These are the electric field lines. That means electric field lines are passing through this small area element. And in this case, the small area element is perpendicular. In this case, this small area element means this small area element perpendicular to the direction of the electric field lines, just like this. The small area element that is del S, that is perpendicular to the electric field lines. The small area element is just like this, and the electric field lines are perpendicular. Electric field lines is perpendicular to the small area element. Then in this case, number of electric field lines crossing through this small area element is equal to 3. Clear? Suppose another case is there. These are the electric field lines. These are the electric field lines, and all are suppose parallel to each other. That means this is the direction of the electric field, and this one is the small area element. This one is the small area element, and here the small area element, in this case the small area element, we write that is del S, and del S is parallel to the direction of the electric field lines. Here del S is not perpendicular, del S is parallel. Here del S is parallel to the electric field lines. Here del S is perpendicular. In first case, del S is perpendicular to the electric field lines. In the second case, del S is parallel to the electric field lines. So that number of lines of force or number of electric field lines crossing through this small area element is equal to 0. That means we get if small area element is perpendicular, number of field lines crossing is equal to 3. If small area element is parallel, number of field lines crossing is equal to 0. And we get number of field lines crossing through this small area element depend upon orientation of the area element. Clear? Orientation of the area element means in this case angle is 90 degree, and in this case angle is 0 degree. Angle 0 degree means angle between this small area element and direction of electric field. Clear? And to represent the orientation of small area element, we considered the area element as a vector quantity. We consider the area element as a vector quantity, and that vector quantity is known as area vector. Small area element, we write that is del S, and area vector, we write that is del S vector. This is the difference. For del S, we write that is the area. Simply we write that is area or area element, and del S vector, that is the area vector. Then what is the direction? What is the direction of the area vector? Because you know, vector means magnitude is there and the direction is also there. And here suppose we take a small plane surface or a small area element just like this. This is a very small area element, and that small area element we write suppose del S. Clear? Then we draw perpendicular to this plane surface or draw normal to this plane surface. This one is the normal, this is the outward normal, and we draw also backward normal just like this. That means two normals are there. This one is the outward normal. We write this one is outward normal. And for this we write suppose n cap, and this is a plane surface. This is a plane surface, and that is a two-dimensional case. That is a two-dimensional case because plane is a two-dimension, and that is not closed surface, that is a open surface. That is a open surface. That means in case of open surface, we draw two normals. One is in outward direction and another is in backward direction. And in case of area vector, always direction of area vector is outward. Clear? That means this is the direction of area vector. This outward normal is the direction of area vector. Suppose another case, we take a closed surface. Suppose this one is a closed surface, and suppose that is a sphere. That is a spherical surface. This one is a closed surface and that is a sphere. This one is the closed surface and that is a sphere, suppose. And here also, in case of a sphere, the total surface of the sphere looks like a curved surface. That is not a plane surface. That means in this case, we take a small surface area, very small surface area. We take a very small surface area, and this small surface area we write that is del S. Del S is the surface area, or that is also known as small area element. Here we write del S, that is small area element, and here we also draw a outward normal. Suppose this is the outward normal. Suppose this one is the outward normal from this small area element. Then direction, for direction we write n cap, because n cap you know that is the unit vector and that gives the direction. And this outward normal gives the direction of small area element. Clear? And spherical surface, that is a closed surface. This is a closed surface. This one is a closed surface. Closed surface means that is three-dimensional figure. This one is a three-dimensional figure, just like your cylinder, your cube, your sphere. These are the three-dimensional case. And in case of closed surface, we take a very small area element, and this small area element looks like a plane, and we draw a outward normal to this small area element, and this outward normal gives the direction of area element. Clear? Then we write area vector is equal to del S vector. Area vector is represented as del S vector, and you know any vector is represented as magnitude of the vector multiplied by direction, and this magnitude del S is known as the small area element. Clear? And this n cap is the outward normal. N cap is the outward normal. That means area is a scalar quantity and area vector to represent the orientation of small area element is a vector quantity. Clear? Then what is the meaning of electric flux? Main heading, that is electric flux. Electric flux. For electric flux, we use the symbol phi. Phi is the symbol of electric flux. What is electric flux? Suppose we take a plane area just like this. Suppose this one is the plane area, and these are the electric field lines. These are the electric field lines. And suppose electric field lines is perpendicular to the plane area or plane surface. Electric field lines is perpendicular to the plane surface, or this is a small area element. Electric field lines is perpendicular to the small area element, then number of field lines crossing through this small area element is known as electric flux. Clear? That means we write electric flux means that is measure of all the electric field lines crossing normally to the small area element. Clear? That measure all the or measure the total number of, we also write just like this, measure the total number of electric field lines crossing normally to the small area element. Clear? Suppose we take one case. Suppose this one is a small area element. We write suppose that is del S1, first case, and these are the electric field lines. These are the electric field lines passing through this small area element. These are the electric field lines passing through this small area element. Clear? And here the small area element is perpendicular to the electric field lines, and in this case total number of electric field lines crossing through this small area element, we write suppose that is 3. Clear? Another small element, we take another small area element but slightly greater as compared to the first one. We write that is del S2. Here we write del S2 is greater than del S1. Clear? Then what happens? These are the electric field lines. And all the electric field lines are passing through the small area element. Clear? And again here suppose we draw another electric field lines. These are the electric field lines. And all the electric field lines are parallel to each other in this case. That means field is uniform. Then in the second case, total number of field lines crossing is equal to 1, 2, 3, 4, 5, 6. Your total number of field lines crossing through this small area element is equal to 6. In the first case, total number of field lines crossing is equal to 1, 2, 3. Clear? That means if we increase the area or if we increase the shape and size of the area element, then number of electric field lines crossing through the small area element is also increased, and total number of electric field lines crossing through this area element perpendicularly or normally, that is known as flux. So that we write from this figure, we write finally flux means here flux is also small, we write that is del phi. Del phi is depend upon the surface area, that is del S. If we increase the area, number of field lines crossing through this area is also gradually increased, just like this, because here total number of field lines crossing, that is 3, here total number of field lines crossing is equal to 6. Clear? Another case, second case. Suppose we take a small area, this one is a small area, and this small area we write that is del S, and we draw the field lines. These are the field lines, and their field lines are diverge with each other, or distance between the two field lines is gradually increased, just like this. This is the first case, this is the case 1, or first small surface area or first small area element, suppose placed at point A perpendicular to the electric field lines. Then we take same surface area, same small area element, that means that is also del S, and suppose placed at point B, and in this figure at point A distance between electric field lines is small as compared to at point B, because distance between two electric field lines is gradually increased, so that at point A, you know, electric field intensity is greater than as compared to electric field intensity at point B. Clear? That means if electric field intensity is greater or more, number of field lines crossing through this small area element is also more. If electric field intensity is less, then number of electric field lines crossing through this small area element is also less. And finally we get the flux, that is del phi. Del phi means that is the total number of electric field lines crossing through the small area that depend upon electric field intensity. Del phi is also depend upon electric field intensity. If electric field intensity is gradually increased, then total number of field lines crossing through the small area element is also gradually increased. Clear? And in this case, this is the direction of the area vector. We write that is n cap. Here also this is the direction of the area vector. We write that is n cap. And the small area element is perpendicular. In this case, the small area element is perpendicular to the electric field lines. This is the direction of electric field lines. And this is also direction of the area vector, because area vector is normal or perpendicular to the surface area. That means this is n cap, this is n cap, and this is also E vector. This is also direction of the E vector. That means direction of E vector or direction of electric field lines and area vector both are in the same direction in this case. So that we write theta is equal to 0 degree. Theta is equal to 0 degree. Theta means angle between direction of electric field lines and area vector. Clear? Suppose another case. Suppose we take a small area element just like this, and we draw the electric field lines. These are the electric field lines passing through the small area element, not perpendicularly, not normally. You are making some angle theta. This is the direction of electric field, and this is the direction of area vector. We write that is n cap, because area vector is always perpendicular. Area vector is always perpendicular to the surface. Area vector is always perpendicular to the surface. Clear? And in this case, suppose this angle is equal to theta. Now, we divide the electric field intensity into two rectangular components. One is along the direction of the area vector, and this component is known as the E cos theta. Another is perpendicular to the area vector, that is known as the E sin theta. You know that. That means simply we divide the electric field intensity vector into two rectangular components. One is along the direction of area vector, and here E cos theta is along the direction of area vector. So that total number of electric field lines crossing normally means that is electric flux. Electric flux means we write that is del phi. Here del phi is depend upon not electric field intensity, that depend upon component of electric field intensity which is in the direction same as area vector, that is E cos theta. That means finally we get electric flux is directly proportional to del S. Suppose this is equation number 1. Similarly, here we get electric flux is depend upon E cos theta. Suppose this is equation number 2, and from these two equations we write electric flux for small area element del S is, we write that is del phi. Del phi is directly proportional to, first one is small area element del S, and the second one that is E cos theta. Clear? That implies we write del phi is directly proportional to, we write just like this, E del S cos theta, same thing. That implies we write del phi is equal to, in place of this proportionality we put a equal sign and multiply by a constant. Suppose your constant is equal to 1, simply we write E del S cos theta. That implies electric flux for small area element is equal to, what is E del S cos theta? You know in class 11, vector A dot B vector, that is equal to AB cos theta. That means this is the dot product of two vector. Dot product of two vector means one vector is E vector and another vector that is del S vector, and this is the mathematical expression of electric flux. This is the mathematical expression of electric flux. That means electric flux is equal to dot product between electric field vector and area vector. And here what is theta? Theta is angle between E vector and area vector. Angle between electric field vector and area vector is known as the theta. Clear? Suppose for the total surface area, this is the expression. This is the expression for small area element. This one is the expression for small area element. Suppose we take the total surface area. For total surface area, then we write the expression just like this. Total flux for the whole surface we write that is phi. Phi is equal to summation of all the small electric flux. That means this one is the electric flux for a small area element, and the total surface divided into large number of small area element. So that we write total flux phi is equal to summation of, in place of del phi we write E vector dot del S vector, and this is the expression for total flux. Clear? And suppose this is small area element is very small, very small means this is small area element, suppose tends to 0. If small area is tends to 0, then in place of this sum we put integral. That means the final expression of total flux is equal to integration, and this circle is known as closed surface. Integration over a closed surface. Closed surface means that is a 3-dimensional case. Vector E dot in place of del S for very small surface area we write that is ds vector, and this is the final expression. This is the final expression of electric flux. Clear? This is the final expression of electric flux. Then what is the unit? Unit and the dimension of electric flux. First one is unit. Unit of electric flux. And we write unit of a flux is equal to, you know the formula for flux. Flux means that is dot product of electric field and area vector. We write that is unit of field. Field means electric field multiplied by unit of area. That implies we write unit of a flux, and that is the SI unit. Unit of a flux means that is SI unit. What is the SI unit of flux? We write SI unit of flux. You know the unit of electric field. You know this formula. Electric field E is equal to F divided by charge, and you know the unit of force. Unit of force that is Newton. That is the SI unit. SI unit of force divided by charge, and unit of charge that is Coulomb multiplied by unit of area SI unit that is meter square. That means we write Newton Coulomb inverse meter square. This is the SI unit. This is the SI unit of electric flux. Clear? Another unit is there. Second unit. We write this is equal to Newton divided by Coulomb multiplied by, this is meter square. Meter square means we write suppose meter multiplied by meter, that is meter square, and this is equal to, in place of Newton meter, you know Newton meter that is known as joule. So that in place of Newton meter we write joule, J for joule, joule divided by Coulomb multiplied by meter. What is joule by Coulomb? Joule is the unit of work, Coulomb is the unit of charge. You know work divided by charge, that is electric potential. So that in place of joule divided by Coulomb we put unit of electric potential, that is volt. So that we write V for volt multiplied by meter. This is the second unit. This is the second unit. This one is the second SI unit of electric flux. This one is the first SI unit of electric flux. Clear? Then what is the dimension? Dimension of electric flux. We write dimension. Dimension of electric flux. For electric flux, we write the symbol phi. Dimension of phi is equal to, you know the formula, that is electric field intensity multiplied by surface area. This is equal to electric field intensity, you know the formula, that is force divided by charge multiplied by dimension of area, and this is equal to dimension of force, that is M1 L1 T to the power minus 2. Dimension of area, area means 2 length, we write L square T0. And dimension of charge, charge means A1 T1. And finally we get dimensional formula of electric flux is equal to, here M to the power 1 plus 0, that is 1, L, here 1 plus 2, that is 3, T, here minus 2, here 0, that is minus 2, here 1, if we take 1 to the upper part, that is minus 1, so that minus 3, A, we take 1 to the upper part, that is minus 1. This one is the dimensional formula of electric flux. Clear? Then two special cases are there. We write special case. First one, suppose theta is equal to 0 degree. Theta means angle between, E vector and area vector, that is del S vector. Clear? And this is the situation. Suppose this one is the small surface area, this one is the area, not area vector, and we write that is del S. Then what is del S vector? We draw a perpendicular outward normal. This one is the outward normal, and this is the direction of area vector, that is n cap, or you also write del S vector. And suppose these are the field lines, these are the electric field lines, and all the electric field lines in this case are parallel to each other, and the field lines is perpendicular to the surface area. These are the electric field lines or electric field, direction of the electric field. The surface area is just like this. Electric field is perpendicular. Electric field is perpendicular to the area, but electric field is parallel to area vector. Area and area vector both are different. Clear? Electric field, look at the figure. Electric field is perpendicular to area, but this is the area vector. That means electric field is parallel to area vector. Electric field and area vector both are in the same direction. Same direction means we write here angle theta is equal to 0 degree. If theta is equal to 0 degree, what is the flux? We write net flux phi is equal to integration over a closed surface. Suppose you take a closed surface, that is vector E dot ds vector. That implies phi is equal to integration of E ds, and your angle is equal to 0 degree, cos 0 is equal to 1. That implies you write phi is equal to, in this case electric field is uniform or constant, so that we take electric field to the outside of integration, remaining is equal to E integration of ds, because in place of cos 0 degree we put 1. That implies phi is equal to EdS. That means flux is maximum. This is the case of maximum flux. This is the case of maximum flux. That means simply suppose this one is your surface area or area, and this is the direction of the electric field. If electric field is perpendicular to the surface area, and we also say that this is the direction of area vector. This is the direction of area vector. This is also direction of the electric field. If electric field is parallel to area vector, clear? Electric field is perpendicular to area. Electric field is parallel to area vector. Area and area vector both are different. Electric field is perpendicular to area, but electric field is parallel to area vector. Clear? This one is the area vector. This is the electric field. Electric field is parallel to area vector, but electric field is perpendicular to area. That means angle is equal to 0 degree, not 90 degree. Angle is 0 degree. If angle is 0 degree, electric field is parallel to area vector. In this case, maximum lines of force, maximum field lines crossing through the small area element. Clear? Second case. Case 2. Suppose theta is equal to 90 degree. If theta is equal to 90 degree, situation is just like this. Suppose these are the electric field lines. These are the electric field lines. And this is the direction of the electric field, E vector. And this is the small surface area. This one is the small surface area, and this small surface area is parallel, just like this. Small surface area is parallel to the direction of the electric field. This is the direction of electric field. Small surface area is just like this, not perpendicular. That is parallel to the electric field. And we draw the area vector. This is the area vector. Because you know, area vector is always perpendicular to the area. We write that is area vector, del S vector. Then, what is the angle? Angle between electric field and area vector. This is the angle. We write this angle theta. Theta is equal to 90 degree. If theta is equal to 90 degree, then in this case, flux is equal to integration over a closed surface. You know the formula, that is E dot ds vector. We write E ds cos 90 degree. Cos 90 is equal to 0. So that finally we get phi is equal to 0. Phi is equal to 0 means no lines of force crossing, no electric field lines crossing through this small area element. And in this figure also, look at the figure. Here this is the small area element, and in this small area element, number of lines of force crossing is equal to 0. So that we write flux is 0. Clear? And this is all about your electric flux. And in the next class, we will discuss about your Gauss law and derivation of Gauss law. Clear? And thank you.